Hello everyone, my name is Sam Lane and I'm going to be presenting a solar PV investment proposal at the Naval Weapons Station in Charleston, South Carolina. So the proposed system is a 20 megawatt ground mounted PV system. The solar farm, as I said, will be constructed on the Naval Weapons Station, Joint Base Charleston. And this weapons station is located near the Cooper River in the town of Goose Creek in North Charleston. There are more than 50 tenant commands across the weapon stations with a current workforce of more than 11,000 military personnel, civilians, and contractors. So it's a really big station. And the U.S. Department of Defense is one of the largest consumers of energy in the world. And so to make domestic energy bases more resilient and more secure in the event of natural disasters or man-made events, the Pentagon is working towards moving to energy sources that do not rely on fuel. And so that's been a big initiative from the Pentagon. There's been several solar projects throughout the U.S. on military bases in the last decade. This project at the weapons station will provide clean electricity to a large portion of the base, aid the Pentagon in achieving its goals of transitioning to independent energy sources, and yield high profit margin for the investor. So some things to point out when looking at this project are permits. So permits for wetlands, since it is near a river, and permits for building on government land, or really land addendums or management addendums for building on government lands. So if you look at the map that we have printed, that I have shown on the slide, the area highlighted in green is going to be the projected site or tract of land for the solar farm. As stated, it'll be about 95 acres. And this land, as of now, is not being used by the weapons station. It is adjacent to the parking lot and close to the nuclear power training unit that is located on the base. As I mentioned in the previous slide, this is not a wetland, so that does alleviate some permits that will be necessary if it was a wetland, and also eliminates any environmental concerns with building, destroying habitats in the wetland. So we don't have to worry about that for this project. There will need to be an addendum submitted through the landowner, which is the Department of Defense. That's already been, the land management plan has already been amended. So this project is approved in terms of the Department of Defense land use at the site. All right, so moving on to the technical design of the system. So just an overview of the technical assessment. So DC capacity, as mentioned, 20 megawatts, be about 95 acres. The tilt angle will be 30 degrees for this project at an orientation of 180 degrees. The ground cover ratio will be 0.3. We'll have a total of 46,410 modules over 9,000 strings and 134 inverters. So the module chosen for this this plant is the First Solar FS430 A series, and then the inverter is a Yosaka Selectria Solar XGI 125. So these are pretty standard commercial modules and inverters. They're nothing too fancy, but they are both efficient and will provide a lot of bang for our buck, so to speak. So the land, as you saw on the previous slide with the map, there's not an issue with land use. There's a lot of acreage in that land tract, probably more than 200 acres. So for this 20 megawatt system, it makes sense to use kind of these mid-tier solar panels and inverters. We'll be using a fixed tilt system, and kind of goes along in that same line. So with the fixed tilt system, we'll be able to keep costs down. We won't have to worry about a tracking system since land use isn't a problem, and we're aiming for that 20 megawatts. We have the 95 acres. The fixed tilt system makes perfect sense in this scenario to keep costs down and still produce the amount of electricity that we want to make. The system will face in the south direction, so it's already lined up well to be facing pretty much directly south, so 180-degree azimuth angle was used. And so facing the southern hemisphere, it's going to get the majority of the sun rays as we're here in the northern hemisphere. So the system will produce 32 million kilowatts per hour annually in year one and be operating at a capacity of 18% in year one. And so moving to the next slide. We have our electrical system output by month. So as can be seen, in the spring and summer months, we're going to be producing a little bit more electricity than in those winter months. Some other things that were considered when we modeled this system in the NREL SAM model are system losses. So shading effects are going to be minimal. So we will have to do some tree trimming and clearing in the lot. So we will make sure that we trim all the trees around the plant, so no shading from anything other than self-shading by the modules themselves in the rows. So that'll be the only issue we deal with there. Those shading effects should be minimal. We'll have some soiling losses, which are expected, and then our typical DC system wiring and inverter clipping losses, and then the AC wiring losses. So all those losses are modeled in the system, and we still had the 18% year one capacity as we talked about. All right, so moving on from the technical design to the financial analysis. The first step in any financial analysis is to look at the system costs. So for this system, it'll be right at 94 cents per watt. That is consistent with the latest studies looking at this past year's average cost for building these type of systems at this scale. It's also consistent with what we expect to spend when looking at the modules we chose, the inverter we chose, the racking system we chose with a fixed tilt, and we'll be able to do this project fairly cheaply. So that's great. Incentives, so the federal ITC, and then the modified accelerated cost recovery system depreciation. So those will be the two incentives that we're really looking at, especially the federal ITC for the investor. So that tax credit will be a 26% tax credit on the total system costs. So the partnership structure will be a partnership flip, which will be 99 to 1. So the investor will own 99%, the developer own 1%, up until a goal IRR of 12%. And so once that goal IRR is reached by the investor, the partnership will flip so that the investor owns 5% and the developer owns 95%. So just to go back to that federal tax credit, so as the tax equity investor, you would be receiving 99% of that federal ITC. And so when we look at the total system cost of 18.8 million, 26% of that will go, or 99% of 26% of that will go to the tax equity investor. As mentioned, the flip year will be year 3 for this deal, and with all that in mind, the net present value for the investor and for the developer are both positive in this case, so that does make this deal feasible, and it also will be rewarding for both the developer and the investor. So the initial cash investment from the tax equity investor will be 27.5% of the 18.8 million number. So roughly a third of 18 million, and then with the remaining 72.5% financed through conventional financing. Looking at the numbers over on the table to the right, we do see that actual realized investor IRR will be 12.25%. So these are great numbers. And of course, we can continue to work and play with the numbers and get the deal that works best for everyone. But I think the model we have set here, it'll work great. So that's the plan. That's the system proposal, and I look forward to hearing from you and working with you. Thank you.